Okay, as in the last video we have discussed about the potential difference in very detail. I have guys made you understand the concept of the potential difference, which was the work done in moving 1 coulomb of charge from higher potential, means from positive terminal to the negative terminal or to the lower potential in an electric field, or you can say work done per unit charge when a test charge Q naught is moved from lower potential to the higher potential against the electric field. Then the work is stored in this Q naught or in this test charge, or you can say unit positive charge, in the form of electrostatic potential energy. And that was very important MCQ, right? In today's video we're going to drive the unit for the potential difference. What will be the unit of the potential difference? We're going to see that today. All right, so as we know that what is the formula of potential difference, that is, it is the dot product of electric field intensity and the displacement. All right, what's the formula? This is, sorry, wait, we know that electric field intensity dot del R will be equal to volt, since volt is the denotation of the potential difference. So volt is equal to, means potential difference. This is for potential difference. Potential difference, that is equal to the product or the dot product of electric field intensity and the del R, which is used for the displacement, and we know that displacement is a vector quantity too, and it is dot product, means when we're gonna multiply these both vector quantities in the product, we're gonna have a scalar quantity. Since when we're gonna remove this dot, we'll be having function between these two quantities, and that will be cos theta, which is the angle which represents the angle between the electric field intensity and the displacement, and the product which we'll be getting in the end will be the scalar quantity, since there is a dot between the two vector quantities. All right, so we know that in the electric field intensity we have discussed in very detail. All right, what was electric field equal to, or electric field equal to, that was the basically ratio of the force per unit charge, test charge, or you can say unit positive charge. There are a lot of names for it. Alright, so electric field was equal to force per unit charge. Now we can substitute this force per unit charge in the formula which we have written above this equation, E dot del R. Alright, so volt is equal to E dot R, which means I can substitute the value of electric field instead of this E now. So electric field is equal to force per unit charge, and we know that the unit of displacement is what? It is meter. Alright, it is meter. Now see, what's the unit of force I have? The unit of force is, we know that is Newton. Alright, and the unit of charge is coulomb dot m. I should write here dot, since it is a dot product of electric field intensity and the small displacement. Right, now we know that Newton into meter is equal to what? It is equal to joule, since we have already discussed this in very detail when we were discussing about the work. Alright, work was equal to what? Work was equal to dot product of force and the displacement. In the result, or as in the product of it, we will be getting the scalar quantity, since we have a dot product between the two vector quantities, and the answer to this question will always be scalar, since when we remove this dot, we're going to have a function cos theta, and that will represent the angle between the force and the displacement. Now see, the unit of force is what? It is Newton. Alright, and the unit of displacement is what? It is meter. And Newton dot meter was equivalent, not equal, however equivalent, and this is the sign of equivalent, right? It was equal to joule. It was equivalent to joule. So now instead of this Newton meter, I can easily write, I can write with no doubt, that is equal to joule. Joule. Alright, per coulomb, same, joule per coulomb. Now this joule per coulomb is equal to what? This joule per coulomb is equal to finally volt. is equal to volt. So the SI unit of potential difference is what? Of course it is volt. Unit of potential difference, that too SI unit difference. So what we have discussed till now, V1 was the formula of potential difference, that is the dot product of electric field intensity and the displacement, right? And as we were driving the unit of it, all right, and there when we were discussing about the electric field, we got to know that electric field is the ratio of the force per unit charge. So of course we have written that too. Now instead of this electric field intensity, I can easily put force per unit charge in the formula. As you can see here, I have put, all right, and we know that the unit of force is what? It is Newton, and the unit of charge is Coulomb, and this meter same. Now in the work, when we were discussing about work, we got to know that Newton into meter is equivalent to joule. So instead of writing this Newton meter, I have written joule, all right, and per coulomb same. So now joule per coulomb is equivalent to volt, and that was the final formula of the, not formula, however, the unit of the potential difference. Now let me tell you the nature of the potential difference. There we're going to have a lot of MCQ. This is the most important MCQ in the examination. Examiner can ask you, what is joule per coulomb equal to? So of course that is equal to volt. All right, wait, what is joule per coulomb equal to? Of course it is equal to volt. So these are most important MCQs, all right. Examiner can ask you to, Newton into meter is equal to what? Newton into meter is equivalent to joule. So there must be a lot of MCQs, right? So let me tell you the nature of the potential difference, by what you can have amazing or paramount MCQs, all right. So here we are discussing about now the nature of potential difference. All right, what's the nature of it? I'll tell you 4 things about it, right? I'll tell you 4 things about it. 1, 2, 3, 4 about the potential difference. Initially, nature of the potential difference, and that there we'll be discussing about the 4 very very important parts, and this is very important in terms of MCQs. Examiner can give you a lot of MCQs from this, all right. So initially, the potential difference is a scalar quantity. Since we know that it is a dot product of electric field intensity and the del R, which represents the displacement, both are vector quantities, and between them we have dot. So in the result, or as in the product of this, we get a scalar quantity. So of course it is a scalar quantity, means it has no direction. All right. Second, it is a dot product. It has a dot product, right? Since we have already discussed, it is the dot product of electric field intensity and the del R, which represents the displacement. So it is a dot product. Thirdly, it has a unit of volt, and volt was equal to joule per coulomb, and that there we can also write Newton meter upon coulomb. Sorry, why I'm writing S, it should be C here. All right, and this we got by F by Q dot M, and this we got by electric field intensity and del R, right? This volt is not only the unit of potential difference, however, it is the unit of electric potential and EMF as well. So it is, this very important point, it is also unit of EMF, electromotive force, electric potential, potential. And of course, the topic we are discussing right now, potential difference. All right. Lastly, it has a dimension that is equal to ml square t minus 3a minus 1. This I'm gonna drive for you in the next video. How did we get this dimension? In the next video we'll be discussing about the dimension of the potential difference. So this was all for today.